Hello. So I'm going to give you the general setup for two-stage estimation method. So first, theta is the main parameter of interest. We are interested in theta only. And theta can be as theta satisfies some moment conditions like this. However, as I said in the previous video, the problem here is if you have moments for theta, then you can use the GMM method. However, the problem here is when you define the moment function, there are some missing information. Here is gamma. You need to know gamma uh, for the moment function to be well defined. However, gamma is not known. If you know gamma, then of course there is no problem. The problem is that you do not know what is the value of gamma. So this gamma is referred to as the nuisance parameter, which means like just annoying parameter. Useless and annoying parameter is but so anyhow, it is we are not interested in what is gamma itself, but we need to know gamma to estimate theta. That is the main problem. Think about you may consider these examples, earlier examples. Say let's go back here. So in the two-stage least square case, the relationship between instrument and endogenous variable is not what you want. You are interested. So for example, you are interested in the effect of x on y, but to estimate that, you need to know the effect of instrument on the endogenous variable, which is nuisance parameter. Partition regression. I just want to know the effect of x1 on y, beta 1, but to do that, you need to estimate the effect of x2 on x1, right? In the first stage, that is, so this is nuisance parameter. And heteroscedasticity and GMM, both are the same. I don't care about the variance. I don't need to know the variance. But when variance is not homoscedastic, the Gauss-Markov theorem does not work. So I know that we could do better if we know the variance matrix. Even though I'm not interested in the variance matrix, to have an efficient estimator for beta, we have to estimate that. Same for GMM. GMM, to have the optimal weighting matrix, we need to know the variance matrix of the moment function, which is not my interest. I'm not interested in what is the variance, but we need to know. And Heckman's two-stage estimator, I am interested in the college premium for women, but to estimate that, I need to know the a woman's probability of working. And finally, in Phillips curve, I just want to see the relationship between inflation and unemployment, but the inflation, to use the correct inflation, I need to know what is the people agents expectation. What is the expectation? And I need to estimate the expectation because it is not in the data. So in all these examples, I'm interested in theta, but I need gamma. I need gamma to estimate theta, or to have a better estimate of theta. So this is the setup. So in the moment approach setup, theta satisfies these moment conditions if you knew gamma. If gamma 0 is known, the true value of gamma is known, then you may apply the GMM estimator, but it is unknown, so you have to estimate gamma first. By the way, you cannot interpret this as an identifying equation for gamma. Gamma is not an argument. So when gamma is given, theta satisfies that equation, right? You cannot say gamma satisfies that equation. That is wrong. Think about weighting matrix. So weighting matrix is not a solution to that function. Just theta is the solution when gamma is given. Instead, then, how can we estimate gamma? There is an alternative moment function. Say gamma can be estimated by another information, another assumption, a moment condition like this. For example, think about weighting matrix. Then it will be epsilon epsilon prime, or and two-stage least square. Then m will be the moments from the first stage regression. So also you can think about where you can identify gamma from the examples, and then so given this and this, now you can imagine how we can estimate them. First, I will estimate gamma from this GMM method. So use the GMM method to estimate gamma from this moment, and then once you estimate, so this and then plug in gamma hat into the moments for theta, and then estimate theta by another GMM method. So the first GMM is the first stage estimator, and the second GMM is the second stage estimator. You may use GMM or least squares, whatever you want. That is not a big difference. But the point here is two-stage estimator. And then, okay, then now think about, so in some of the examples earlier, I told you that you may estimate the model in one step, like two-stage estimator, two-stage least squares estimator, instrumental variable estimation can be done as just GMM, which can be done in one step, or partition regression can be done in one step, and Heckman's two-stage estimator can be done in one step, and there are many examples where you may do it in one step. So two-stage estimator could be done in one step if you think about this. Suppose that the parameter, like we have two parameters, the parameter of interest theta and nuisance parameter gamma, and say define pi as the combination of them, or like all the parameters we do not know in the model, and then also combine the moment functions. G is the moment for theta, m is the moment for gamma. So then combining them, we may define another moment function h. H is the bigger moment function. So then now you may interpret this setup as an estimation of pi using moments, all the moments h, right? So I collected all the moments into h, collected all the parameters in pi. Then after the collection, it's just one parameter vector and one moment factors. So you can just estimate pi from this moment function. It is possible in some cases. Often it may be difficult. So obviously, because it is difficult, we use two-stage. So going back to the example, think about the partition regression. You learn this in textbook, but no one uses partition regression in practice because one-step estimation is easier. OLS is easier. Just include x1 and x2 at the same time and estimate beta 1, beta 2 at the same time. That is much easier to obtain beta 1. So you don't need to do two-stage estimation. So like that, usually two-stage estimator can be implemented in one step, but one-step estimator is usually computationally more difficult. For example, derivative becomes larger, or variance matrix becomes larger, so maximization becomes more complicated. So it is possible, but not useful. That's typical reason why we are doing the two-stage estimator. Okay, then what is then of course there may be some cost of doing two-stage. Like I told you, one-stage estimator would be better if it's computationally easy. But then what is the price of doing it in two stages? Typically, the variance estimation. So just maximization or estimating theta will be easier in two steps because you break down complicated maximizations into two steps. But then the problem here is, how can we estimate the variance? Variance will be much more complicated. So the main problem here is, the important intuition here is that when you estimate the first stage, the result of the first stage estimation has its own estimation error, right? Obviously, there must be estimation error in the first stage estimation. So the first stage error will have some effect on the second stage result. So the standard error, for example, if your first stage method is inaccurate, then no matter how accurate your second stage estimator is, still your second stage will be inaccurate just because your first stage is inaccurate. You understand? So if you use very a perfect estimation method in the second stage, however, if the first stage method is not good enough, then because of the first stage problem, your second stage estimator will have the same problem, even if the second stage was near perfect, right? So that is reflected in the standard error. The first stage estimation error must be reflected in the standard error of the second stage estimator, the final estimator. However, it is usually more complicated, and many students, many researchers just ignore that for different reasons. Many maybe just because of their ignorance, or maybe because it is too much complicated. They don't know how to do that. Both are bad, of course. So think about these two different cases. So two cases. Suppose that you know the true value of the nuisance parameter gamma, versus the second case, you estimate gamma from the data in the first stage. So in the first case is usually called an infeasible method. It is infeasible. You don't know the true parameter in reality, but just assume. Even though it is infeasible, we are going to consider this. So if you know the true value of the nuisance parameter, you don't need to estimate that, and there is no error in gamma. Gamma is always correct. So you just need to do the second stage, and this is the feasible case, feasible method you are going to use gamma hat, but gamma hat may be wrong, right? Gamma hat may be wrong and may have estimation error, and then using those potentially wrong gamma hat, you are going to estimate theta, the final estimator. So from suppose that the second stage method is the same for these two cases. However, the second one will be less accurate in general, right? So because there is an additional error, potential error in gamma hat, which does not exist in the first one, in the former one. So if you ignore these, usually the first stage estimation error is ignored, then you are considering this case, which is different from your method, and usually the standard error is underestimated because some error is ignored. So you are underestimating. Your estimator is not that much accurate, but your estimation, your standard error calculation is wrong, so it looks like it's accurate, which is dangerous. You are not doing well, but you got a good standard error. So that's a problem. However, it is just intuition. I'm just saying that this principle in general, mathematically it is not true. Mathematically, it could be the other way. And interestingly, in some rare cases, if you ignore the error in the first stage, then the standard error may increase. Even if you ignore the estimation error, your standard error becomes larger. And one of the rare examples is two-stage least squares. So I'm telling you, like in this course, two-stage least squares, like for the instrumental variable, is our main model, but it is not general model. It is one of the rare examples where you are ignoring the first stage estimator. So case B has smaller standard error than case A, which is really counterintuitive. Let's see, but it happens. It can happen, but just our intuition tells us this way. And in general, they are different. At least maybe this may be large or this may be large, but usually they are different. So you have to consider the first stage estimate. And then if you underestimated the standard errors, then it is actually it's a serious problem. Because you think your estimation is not significant, but you may mistake it as a significant result. So your conclusion may be wrong. So think about the other case. If your estimation was actually significant, but your standard error was misleading so that it looks like insignificant, that is not a big problem, because if your result is insignificant, you are not going to claim any conclusion. So you cannot get any strong conclusion. So anyhow, it won't be a big problem. So you did not find something because of your mistake. But if you underestimate standard errors, it is a bigger problem. You are claiming something that does not exist. So this is a bigger problem that like not finding anything. So it is just so as a researcher, you have to be conservative, and your conclusion must be based on significant results. So this principle was broken if you underestimate standard errors. So it's serious problem. Okay, I will do the math in the next video.